Thank you very much. So, hello everybody. My name is Luis. He is Jorge. We're both together working at the National University of Mexico in Campus Cuernavaca officially. So the subject of our talk is this package we have built together, which is called Taylor Integration. So Taylor Integration is an integration method for ODs, which is very particular in the sense that you want to use it if you look for accuracy. And when I mean accuracy, means high accuracy. You're not only content to have 3 or 4 digits, you are pushing it really hard. So when at all you actually care about those things? So let me just present an example that may be interesting for you, which is this guy called Apophis. So can you see this moving dot somewhere over there? So that guy is a rock of 300 meters across, which was discovered in 2004 in some Italian observatory. Now, the important thing that maybe one should be aware of Apophis is that its Keplerian elements of the orbit are very close to the Earth. And if you actually take a look on the aphelion and the perihelion, that's it. That's the furthest distance from the Sun and the closest distance from the Sun. It actually crosses the orbit of the Earth, which is at 1 AUs. So we should care a little bit whether it crosses or not our orbit. And in that case, 10 to the minus 4 may be crucial. So you don't want to be in the accuracy of having only trust in 4 digits, but maybe 13 or 14 or even 15. So just to keep you updated, the next important encounter will be April 13, 2029. And just as a side comment, April 13 is Friday. So if whatever makes it important. Anyway, so what I will do is explain a little bit the maths behind the method. Then Jorge will describe a little bit some of the examples. And he will, show you whether you should or not bring your umbrellas a priori on April 13. So the whole idea of the method is the following. You have a differential equation, which is written here, and an initial condition. Now, this initial condition a priori is the orbit of this NEO. And you approximate the solution locally by a Taylor series. And please notice that there is no upper limit in this polynomial. So a priori is the solution what you are using. So the whole thing is simply to substitute this equation back into the differential equation, then use that the right-hand side of the equation, you can also express it as a Taylor series, and then in 2 lines, you come to this recursion relation. So this is the way you can actually construct the exact solution. So if you know the Taylor series of the right-hand side of the equation, you simply have to divide by the order plus 1, and then you get the order plus 1 term. Now, the way we do it in the package, it is that this Taylor series of the right-hand side of the differential equation, we generated numerically using, actually exploiting TaylorIntegration.jl, which was developed by me and also by David Sanders. It is still under development. Now, but you cannot compute with the actual solutions. You have to truncate it. So something neat about Taylor series is that whenever you truncate the series, you can actually bound the error that you are making by that truncation. But you do not want to truncate it too soon. You actually want to truncate it once you are in the convergent tail of the series. And if you are in that convergent tail, then you can actually estimate a bound for the time step that your integrator may perform. Now, to be sure that you are on the convergent tail, then you have to go to high orders of the Taylor expansion, which means not to stay on order 4 or 6 or 12 or 16, but maybe to go up to 30. And I think we do not usually ask students in Calculus 101 to calculate the 30 derivative of absolutely anything except for the exponential. So I will stop right here because this is the essence of the method. I truncate the series at a very high order, and then I get some sort of step size which will be adapted each time I reconstruct the local time series. And I will speak now about a slightly different tool which is built also in our package, which is the so-called, the example. So this is the blackboard, Calculus 101. This differential equation, we all see it and can solve it. This is the exponential of minus t. And what you simply recognize is that the right-hand side is actually the dependent variable. So f, the Taylor series of f, except for a sign, will be the Taylor series of x. Now you plug that in into the recursion equation, you do a couple of things, and you end up with this expression. And that expression is the k plus 1 term of the exponential of minus t. So you are done. You are very comfortable in the sense that you are actually getting what you should. Now, the issue comes when you are using floating point numbers. So you have to be very close to this thing. And very close, in our case, will be obtained through automatic differentiation techniques. Now, the other tool I was mentioning before, it is so-called jet transport, and I think this is absolutely unreadable, so I apologize for this slide. But the idea is, let's not only integrate one single initial condition, but actually a bubble in phase space around that initial condition. So when that bubble is sort of moving along the flow, that bubble will be actually the form and adjust to the actual flow of the dynamics. So this is like an equivalent of an infinite an infinite number of trials within a Monte Carlo simulation, because you have the whole volume within that bubble. So more or less the idea of the method is the following. Let's keep now the harmonic oscillator in mind for a second. So the whole idea is that you have an initial condition. And around that initial condition now, I will use Euler's method as an example because it does not depend on Taylor's method, but it will require some polynomial manipulator. But so aside from the initial condition, you simply consider tiny little deviation in each one of the independent directions, which are these delta x, delta y. And you plug it into your integrator, in this case, Euler method. And after 2 lines of very simple mathematics, you see that this first term is actually what you would get directly from using Euler's method into the initial condition. Now, the next term, this matrix, is actually the solution of the first variational equation. So, and you see that it will be some sort of polynomial on delta x and delta y. So if you consider higher order terms, which is to plug it in back in a couple of times, then the complexity of this term, the corrections, will be polynomial, will be a more complicated polynomial on delta x and delta y. The point is that your solution can be written as some sort of time-dependent path, which is your time step here, and the coefficients will be now polynomials on these delta x and delta y. So if you teach your integrator how to manipulate polynomials, a priori this is a technique you can incorporate. So now Jorge will be describing lots of examples of what we have achieved with our high accuracy integrator.
Okay, so as a first example, I'm going to talk about the Lorentz system. So everybody knows this system. So using Taylor integration, we are able to just write the equations of motion and also select an initial condition, initial and final time. And then using this TaylorInteg command, we are able to to get the solution. So here I'm plotting, the Lorentz attractor, and we have been trying to do an interface which is close to what differential equations has, in order to have a common interface. So okay, so some other things that we're able to do with Taylor integration is to calculate the Lyapunov spectrum of dynamical systems. In this case, I'm showing also the Lyapunov spectrum of the Lorentz system, and so using this function, we're able to calculate actually the Lyapunov spectrum. Now, how sure can we be that this computation is accurate? So, sorry. We know that for the Lorentz systems, the sum of the Lyapunov spectrum has to comply with this property that it has to be equal to the trace of the Jacobian of the right-hand side of these equations of motion. So at the end of our integration, these are the values for the Lyapunov spectrum, and this is the exact value of the trace of the Jacobian for the Lorentz system. And this is the result we get for the sum of the Lyapunov spectrum. So it's really close to the exact value. Oh. Okay. So some other things that we are able to do is, for example, the Henon-Hayles Hamiltonian. We integrate it, so we are able to get the orbit. In this case, I'm plotting a periodic orbit of the Henon-Hayles system. So how accurate is our solution? Well, we know that autonomous Hamiltonian systems must preserve the energy. So here I plot the energy as a function of time, and what we can see is that the energy is preserved up to very little errors, which are comparable to the machine epsilon. Okay, and other things that we can do in order to study how accurate our solutions is, for example, again, for Hamiltonian systems, we know that they have to comply with a symplectic structure. So we are also using Taylor integration. We are also able to evaluate this property, and what we can see is during our integrations, we are able to be very close to the symplectic structure and only get errors which are comparable again to the machine epsilon. Okay, so as an example of an application, I will show a construction of the Poincaré map for the Henon-Hayles system. So here I take several trials around the specific orbit of the Henon-Hayles system, and okay, so we integrated, and then we can see that an initial bubble over the Poincaré surface of section returns again, and the iterates of the initial set of conditions evolves over the Poincaré surface of section, and we can do this at once. Okay, so here's a sum over a 5 periodic orbit, and each one of these points represents an individual orbit, and each one of these preserves the energy up to machine epsilon variations. Okay, but that was a Monte Carlo method around a 5 period orbit, and now I'm gonna show how we can do the same, but using jet transport techniques. So once again, we integrate our system, but this time we construct an initial condition, which is a polynomial in the deviations around the reference initial condition. So this initial condition, we put it into the solver. Oh man. And so, what?
What kind of object is the side?
Oh, it's a multivariate polynomial. So, yeah, that is implemented in Taylor series. Okay. Okay, so now I'm showing again the Poincaré map for the Hainaut-Hillis system, but only this time we actually built this cloud of initial conditions using jet transport. And are they similar? Are they not? You know, the Monte Carlo versus the jet transport? Well, let's see. So that's again the zoom, but it's using jet transport. Jet transport is the orange line versus the Monte Carlo process, which are the blue dots. So this is a third order jet transport, which is able to reproduce the dynamics around this orbit. Okay, so now about Apophis. Okay, so we constructed a model which includes all the planets, the sun, the moon, and the dwarf planet series. We include several physical relevant effects. And okay, so here is just a plot of the inner solar system where we can see the sun, Mercury, Venus, the Earth, which is the orange line, and the blue line is the orbit of Apophis. So, okay, this is a plot of the geocentric orbit. That means with the Earth in the center, we plot how Apophis moves. So, okay, what we can what we can see here is that it is the Earth is this dot. Perhaps it is not so clear here, but it's usually pretty far from the Earth, but at moments it can get pretty close. So here it is. Whoa. Okay. And yeah. So okay. So here's a zoom of that last plot. So what we can see is a 2029 event. Apophis is gonna be really close to the Earth. It's gonna be several times closer than the moon. And okay, well, so how good is our orbit? So for this integration, we took initial conditions on 2007, and we propagated all through 2029 and beyond. So we comparated our integrations with observations from the Arecibo Observatory in Puerto Rico, and this is what we got. The orange crosses are actual observations, and the blue line is our integration. So, okay, now we compared our integrations versus the NASA JPL predictions. So we were able to reproduce the prediction from JPL up to very little variations. For example, for the time of maximum approach, the difference in our integration versus JPL's prediction is less than a second. And in distance, the difference is less than, I think, 12 kilometers. So this difference is actually well within the 1 sigma uncertainty in this in the JPL prediction. So okay, so now how close is gonna be Apophis? Okay, so we built this plot. So we are we are plotting the Earth Apophis distance versus time, and what we can see here is that we have to zoom a little bit. So the green line is a lunar distance, is the distance to the moon. And this is Apophis. We have to just a little bit more. Just the last zoom. Okay, now that this purple line is actually the Earth radius. So 0 means the core of the Earth. the purple line means the Earth surface, and this is apophysis. So it's going to be really, really, really close. But it's not going to hit at least on 2029. Now the thing is, that after that, since it's going to be really close to the Earth, then its orbit is going to be greatly perturbed. So that generates a new problem. So we have to be sure that our reintegrations are very accurate in order to be sure that we are reproducing the actual orbit of the asteroid. So
So I will skip for a minute or two the conclusions and the to-dos, because we were a bit afraid that time was not going to be enough. So what I will present are very, very, very preliminary things that we have been playing around. So I am loading now interval arithmetic and half floats. And the only thing I will do it is plug that in directly into the integrator. So sorry. So I will integrate exactly the same example that David was showing. So this is the function t square, and I will be integrating it from a time. This is the initial condition, an interval of which is 0. This is the initial time and the last time. So from 0 to 1 t square. It should be t to the third over 3, evaluated in 0 and 1 gives 1/3. And we will be using a polynomial of order 20, and this is the absolute tolerance I was describing at some point. And without doing any specialized method, the answer I get is written here. So the interval that contains 1/3, not the floating point 1/3, but the actual true number 1/3, is within this thing. So the actual computation we have performed of that integral in actually one single step of the integration. Now, if I do exactly the same thing with R floats, it turns to be identical. So please notice in the lowest line that at time 0 I'm on 0, as it should be, and whatever is time equal 1, I get the answer in one single step. Now, this is actually cheating a little bit, in the sense that I am using a polynomial integrator, and the solution is a polynomial, and I am using a polynomial of order 20. So for sure, I have to hit t to the third over 3 at the first. So let's redo this with sinus of t. Sinus of t from 0 to pi. I'm not sure whether it is seeable, this, but well, from 0 to pi, again an order 20 polynomial and a very tiny absolute tolerance. I do the integration and I get this value, which contains the true 2. I mean, 2 is also a correct floating point, but look at the size of this integral, So it is 10 to the minus 15 or something like that. So even though we have not implemented a validated integration, a rigorous integration that contains the true solution, for these two cases at least, we get it for free. So now, let me go back to the conclusions. So with Taylor integration, you can achieve very high accurate integrations of ODEs if you are actually looking for that. So if you're content with whatever gives you Euler or Runge-Kutta of order 2, I mean, you should stay away from Taylor integration. But if by some specific reason you need 10 to the minus 14 in accuracy, you should maybe take a look on this. Now, it interacts nicely with other formats of numbers like intervals and ARP floats. It is slow because we actually do not care about performance, we care a lot about accuracy. And if you do care about accuracy, maybe you can take a 15-minute coffee break or something like that, come back and look for your results. Now, there is actually room for improvement on these things. So I will mention some. So we should actually build a common interface or to be able to be called from Julia diff equations. It would be nicer to make a softer way of implementing a Monte Carlo calculation, which actually relies on Taylor integration. We can improve performance, and to do so, I have some ideas which require some meta-programming wizardry, which I am not able to do. There is still work in process, which was already shown. This Poincaré surface of section, it was not mentioned, but actually you can be sure in 10 to the minus 16 that you are crossing the surface of section. It is not interpolating in 2 points. It is not doing any trick, but actually finding the true cross on the Poincaré surface of section. And there is a little bit to do actually to get into this validated numerical integrator. So we are actually working on that, but if you want to join us, you're welcome. So thank you very much.